right. We're back with another great panel. We're closing out our Heat Pump Water Heater Day strong. Thanks for sticking with us for all these great educational sessions. Today, we're going to be talking about residential, commercial, and heat pump water heater load shifting lessons from the field. Similar to a couple of our other sessions today, this session is sponsored by the San Diego Learn program that offers these free energy efficiency and electrification webinars and other resources. Please do check out their website that you see online. Today's session is, I'm just going to introduce our moderator. My colleague, Noah Gabriel, is a senior project analyst at NBI. Noah manages multiple projects, most related to water heating, research and deployment, and is an all-around great guide. Noah, over to you, and I'll keep the slide up as you introduce your panel.
Awesome. Thank you so much, Joe. And unfortunately, on the background image, it's giving me a "you don't have permission to access this" error. So I guess I'll proceed without it for now, but I will say I love the backgrounds and terrific work on that. So yeah, I'm thrilled to introduce some awesome panelists today. Several people who are both industry experts and really leading the way through various pilot programs, research initiatives, and just other means of driving the load shifting market forward. Just as a quick introduction, I think this is going to be covered later, but one of the most amazing things about heat pump water heaters is their ability to act as a thermal battery. So as others have mentioned in previous panel discussions today, there's a bit of a trade-off. You do have lower electricity usage and therefore lower power, but you make up for that in having generally larger storage capacity. And that makes it really great to be able to use energy when we want to, as opposed to just when the water heater is turning on. You can basically store energy in advance and take advantage of solar and wind energy and really help to integrate those non-dispatchable resources into the grid. So with that, I will introduce Geoff Wickes, who's a senior product manager at NEEA. Geoff has extensive experience in this industry and is going to give us an introduction of kind of the background of CTA 2045, which is the load shifting standard for heat pump water heaters, or one of the standards. We also have Peter Grant, who works at the Berkeley National Lab, and I've worked with Peter on several occasions doing heat pump water heater research for load shifting. Peter is great at writing algorithms to do custom load shifting work. And then also Amélie Besson, who is the manager of programs at NEEA. Amélie runs one of the biggest heat pump water heater demand response programs in the US. So I'm super excited to have all of them on. And with that, I will turn it over to Geoff.
Great. Thanks, Noah. I don't seem to see the button to move on to the slide deck, or did you want me to present mine?
Yeah, if you don't mind sharing your own screen, that would be awesome.
Okay. Just trying to see where that is on here. This is...
No problem. I can pull it up for you if you...
No. I thought you had asked for it, so I just... Okay. So welcome, everybody, and thank you, Joe and HWPH for celebrating Heat Pump Water Heater Days. How's that view look?
Yeah, Geoff, so just hit the full screen presentation mode, the little presentation icon near the top left, two over from save. Perfect.
And then hold on a second. And are you seeing the full screen now?
I swap presenter view and slide.
Yeah, there we go. Okay, I just want to make sure.
Perfect. That's great.
Okay, so you got some exciting stuff to hear from both Peter and Amélie, but I'm going to give you just a brief background on what heat pump water heater connectivity is about and what we've done over the years. So I'm going to cover these topics today, and why do we need flexible loads? What are the services that water heaters can provide? How did connectability water heaters come to be, and how should we connect to water heaters? And what should I do to get connected, and what's my next step? This slide is a fun one that a colleague and friend of mine, Tristan DeFondreville, has created, and it's the California ISO, and it's showing what what happens at their grid on a couple days. This was a couple years ago, but it shows where these peak grids are, where the CO2 levels are, where the steepest ramps are, and where we've got different time of use rates, both in the evening in the early afternoon, as well as the morning. The morning should show up anytime now. There we go. So these are the times when rates are the highest for our customers. And you can see how this ramp could be filled with the integration of the solar. And some days it's bigger and larger than others, or it's sometimes over a slope of time. So you can figure that out. And that's one of the beauties of using flexible load management. But we're really trying to focus in on this time between 3 and 9 p.m., which happens to be the highest period of time. And those gaps need to be filled up or moved out of that area and moved into areas where renewables are more prevalent or cheaper prices are available. So this is a great example of what we need to be doing. This is what some of the benefits and the assets of heat pump water heaters. I make the analogy to a battery. They're not exactly, they don't fill the grid with power, but they can store energy, shift energy, shed energy, absorb the energy at the right time, level out energy use, and then it can also provide ride-throughs during blackouts and that sort of thing. The graphic on the right there was put out by LBNL, and it shows what are the different time periods, and it goes from years on the left side down to seconds. And we really think water heaters belong in this shape, shift, and shed. Shimmy, not advice. We'd recommend other products for that, and that could be inverters or batteries or chargers and that kind of thing. But this is a great example of how heat pump water heaters can be used in these different applications. This water heater you're looking at here was the first generation General Electric higher product that was 120 volt. It was actually shown in January of 2020, and it was a fully enabled, granted with their dongle system, as you can see in RJ45, with it connected to a DC module for CTA 2045. So these are some general concepts, and I'm not going to read these all to you, but flexible smart loads, controls, communication architecture, and grid indication are really key to all of these elements. And we like communication architecture like OpenADR, IEEE 2030.5 or CTA 2045, and we'll talk a little bit more about as we move forward. Opportunities here are applying these tools in a market transformation way. So we have an intervention with lasting change, and it allows our nation to move from a prior, top-down approach to more of a distributed energy management methodology and maximize the use of efficient products at the right time and the right place. So it's the integration of intermittent resources, generally referred to as renewables, and it targets demand response. It also has a load building and balancing methodology, and it avoids systems costs, so we don't have to have increased wire sizes or transformers, and it adds some grid resiliency and reliability for our customers. So as we talked about this already, but this next slide really talks about the value of energy efficiency, hence heat pumps, and we recommend that reduces it all substantially, and then shedding that load, so moving it from one period to the next, and then shifting it from one period down to another. So I don't know if people remember a couple years ago, California was going through a severe heat wave, and the governor there did a voluntary request, and they actually knocked the peak off by, I think it was 2,500 megawatts, substantial. But that's that shifting or shedding. That's more the shedding. The shifting is we need to move this into a period when we have more power and it's not being used. I wanted to give a little bit of a background on what has happened with CTA 2045, or what we now refer to as EcoPort. So starting back in 2013, CTA and EPRI developed this standard, and it went into initial testings in the early days. Then pilots were done through 2021. Bonneville was one of the big ones that I worked on. We can talk a little bit about that later on. And then we're now getting into the next generation of CTA 2045B, and was published in 21. We saw AHRI 1430 approved, which was the standard that all the manufacturers agree to, which basically points to CTA 2045B. JA13 is a California-centric requirement, which requires water heaters to load up their time of use rates as they go into an installation. The challenge comes is when you've got to maintain a clock crystal and or clock timing and or time of use rates change over time. The EcoPort brand was also spawned in 21, and then Oregon, Washington had a statutory requirement to require CTA 2045 on all water heaters, 40 gallons, electric water heaters, 40 gallons up to 80 gallons. Other states are following, and we're now starting to see programs rolling out in not only the Northwest, but across California, Colorado, Massachusetts, Maine, all across North Carolina and New York. And we see it in the future, DR communications being required by DOE code. They didn't do it in this last rulemaking session, which goes into effect for residential water heaters in 2029, but I think they're going to start having that in the future. So I wanted to chat a little bit about connected water heaters and case studies. Now, how am I doing on time? I don't have a clock in front of me right now.
Yeah, no worries. You have a few more minutes.
Okay, I think I've got 2 more slides. So what we did in the Northwest, we started changing our advanced water heating specification to require CTA 2045 and BPA, PGE. We did a big demonstration of 278 water heaters connected, and they were mostly done through a self-install. I think all but 10 of them were done by the individual participants. And over a 270-day period, we ran 600 events, and we had minimal to no complaints. This led to the Oregon and Washington requirement of CTA 2045 ports. So that helped substantiate what needed to be done, and then consequently, AWHI and AHRI 1430 became a relevant conversation, and that's what we enacted. A little bit about the ecosystem. You can see the CTA 2045 port there on the right on a standard smart grid water heater. So utilities have a conversation with not only customers, but also a water heater. Customers have a conversation with their water heater, and OEMs have a conversation with their water heater and their customers. But in this ecosystem, there are a couple different pathways. There's Wi-Fi, there's OpenADR, and or there's CTA 2045. It's not an or, it's an and. We believe that all of those should be there. And much like we all think of how we run our Wi-Fi, I bet you nobody thinks about IEEE 1802.11, which turns into Wi-Fi. And much like what we've done with Wi-Fi, we have CTA 2045 turning into EcoPort. So my last slide here, just wanted to talk about what's next and what can you do. I didn't interlace too many of the transformer motifs into here, but here's one sitting on top of a new water heater. We believe that the future is a new enrollment sticker that go on every single water heater made at the factory. We don't have a specific design yet pulled out, but we're running a study on that right now, and that will enable an installer and a customer to enroll utilities to enroll customers, and it would be a virtuous cycle of enrolling not only the water heater, but customers, utilities, and starting up programs. That's a much more complicated conversation. Happy to do it. We want to encourage utilities to stand up these programs quickly and soon. The information's all been proven. We don't need to spend more time with pilots. We also recommend installing larger tanks and adding some thermal mixing valves just to increase the capacity of these grid-enabled batteries. And if you're an installer, understand how you can provide value-added services and or to your not only to your utility, but to your customers. And then configure your water heater, both either through the app or through your connected device to heat water at the optimal time. And then, of course, share positive experiences of why this improves both efficiency and flexibility. And then here's my last slide. If you need to get a hold of me, these slides will be available, I'm assuming, Noah, so you can share them as you will.
They will indeed. Yeah, thank you so much, Geoff. That was an awesome overview. And we'll have some time for questions at the end. So if anybody has questions for Geoff, just keep them in your mind and put them in the chat either way, and you'll have time at the end. With that, we have Peter Grant next.
Thank you, Noah, and thank you, Geoff, for that great introduction. I'm pulling my slides up. Noah, can you confirm or deny that my slides are currently up?
Looks good to me, and you're in full screen.
All right. Thank you very much, sir. Yes, so I guess one quick comment is that I somewhat regret the phrasing I use on this slide. I wish I had said empowering instead of enabling, but I'm here to talk about some work that we at LBNL have done developing advanced control algorithms for load shifting with heat pump water heaters, and I'll talk a bit more about how they're advanced later, and how we're how we're developing these controls to be something that's fairly easy for utility programs to deploy in the field, and how we are beginning the technology transfer efforts. And then I'll pass it over to Amelie to talk more about her work and partly about that. So our work was done in the context of Berkeley Labs' Cal FlexHub and Store for Build projects. And Cal FlexHub is a big consortium among academia and industry, really around how we can, or determining how we can shift electric loads in response to electricity prices. Right, so we're looking at all sorts of technologies, including cooling, electric vehicles, fans, pool pumps, and heat pump water heaters. And this is done in the context of highly dynamic prices, where you could envision that customers receive a real-time price for electricity every hour of the year. And then since people actually like manually managing their buildings in response to that would be overwhelming, and I think we can all agree that would not happen, how do we design and deploy control algorithms that receive these prices and then automatically shift load to do the best thing for the customer all on their own? That said, that the algorithms don't have to be applied specifically to highly dynamic prices, right? Something that works for highly dynamic prices will work just fine for time of use rates. And so it could be deployed in ways, or the algorithm could be used to create schedules or control strategies for one utility time of use rate versus another, and just help provide flexibility for people in that way. So that developed LBNL's control algorithms. And then afterwards, we started the Department of Energy funded Store for Build project, which looked at deploying these controls out in the field and gathering field monitoring data, as well as technology transfer efforts. So this is heat pump water heater day. Presumably everybody knows at least a little bit about heat pump water heaters, but these are some pretty key details that come in, or that you have to know in order to make sense of load shifting controls. First off, these products have about a 1.2 kilowatt thermal, right? That's heat added to water, not electricity consumed heat pump. It's more on the order of 450 watts electricity consumption. Then there is a condenser coil wrapped around the outside of the tank through which hot refrigerant passes, and then that turns into heat transferring through the walls of the tank into the water. So if you look at the schematic on the left, that's the yellow tube that's kind of spiraling down. Then these products also have 2 to 4 kilowatt electric resistance elements. Sorry, they have two roughly 4 kilowatt electric resistance elements, one at the top of the tank, one at the bottom. That's true for the 240 volt products, but not as true for the retrofit ready 120 volt products. And then these products now have both CTA 2045, which Geoff just talked about, and some have API communication. And these different communication protocols enable you to send load shifting control signals so that you can change the timing of electricity consumption in the water heaters. They also have roughly 190 to 303 liter, which is 50 to 80 gallon storage tanks. So as Noah was saying, these are thermal batteries. There's energy storage available. And since we have these communication and capabilities, and we have this thermal energy storage, really we have everything that we need in order to shift electricity consumption without the occupant ever noticing. Nobody's less comfortable because of this. All we need to do is figure out how to use these capabilities intelligently to deliver good results. So I'll skim over this one pretty quickly because Geoff talked about CTA 2045, but it's both a hardware and software standard. So, there's the communication capabilities are specified, and there's also the plug that comes in the water heaters, as well as the shape of the module that can be plugged in. These have the signals that you need to both increase and decrease electricity consumption. The key signals that we're really using a lot are the load up, which tells the water heater to activate the heat pump and bring the water to the set temperature. Then CTA 2045B, I'll come back to why that's important later, but CTA 2045B includes the advanced load up command, which does everything load up does, but also increases the set temperature. So you can dramatically increase the amount of energy stored in the tank in this way. And then it also has a shed command, which essentially tells water heater to delay heating the water longer than it normally would. And so if there's a peak period or a high electricity price period, you can coast through it a little bit longer without consuming electricity and hope to make it all the way through. Whereas without the shed, you might not. So when I started working on load shifting for heat pump water heaters, our first field study was in 2020. And back then, the typical strategy was to create a single engineered solution of CTA 2045 or API signals and send those signals to all heat pump water heaters in the fleet, regardless of occupant behavior, and only in response to a single time of use rate schedule, right? So I'll come back to the behavior in a moment, but you could envision that creating this engineered solution took a while, and as time of use rates change from one part of the state to another or to a different state, or as they just change from year to year, there's a lot of effort that's required to create this new engineered solution over and over and over. Avoiding that would be great. Then if we look at the plot on the right, that shows 3 sample heat pump water heater, hot water on the top, and electricity consumption curves on the bottom. On the top, you can see that the green heat pump water heater consumes a lot of hot water early in the morning. It's enough to turn the heat pump on around 7:30 or 8 a.m. And then actually the heat pump can't keep up, so it turns the resistance elements on around 9 in the morning, right? So that's one use case. Then the blue one shows very similar, but in the evening, where there's so much hot water consumption in the evening that it has to use the electric resistance elements right during that evening peak or high price period. And then the third case actually has 0 hot water consumption. Presumably somebody's on vacation that day, and the heat pump just activates for a short period twice throughout the day to make up for jacket losses. So I think you can look at these plots and realize that these 3 different cases would really benefit from 3 different load shifting control algorithms, right? The green data would benefit from an advanced load up at roughly 5, maybe 6 in the morning to increase the energy stored in the tank and be able to not use the resistance elements, but only use the heat pump in the morning. The blue one would benefit from an advanced load up late in the afternoon to again avoid using the resistance elements, but also maybe be able to shift the load from that evening peak to the midday period. And then the red one, I mean, all we can do is make that worse, so we shouldn't send any load shifting signal schedules to that one at all and just let it do its thing. And so that problem is really what inspired a lot of our work in CalFlexHub. So we developed a control algorithm that creates customized CTA 2045 or 2045B signal schedules. It uses the provided electricity price profile, which could be a highly dynamic price, or it could be a TOU rate schedule. And then it creates customized CTA 2045 signals schedules that minimize the cost of operating heat pump water heaters. Then coming back to the behavior, since there's a broad array of how people consume hot water in different houses, we break them into groups with similar baseline behavior and then create a single signal schedule for each group. And in that way, we can kind of identify the high morning users versus the high evening users versus the low users and generate the different schedules like you see in the plot on the top. Now, this can all be pre-computed, which makes it fairly easy for a utility program to just do the same thing. And they get their data for their water heaters in the field, put it into the algorithm so they get the group. And then once they get the group, they can put in their price curve and get out this appropriate signal schedule. Now, this plot right on the bottom is simulation, unfortunately. We don't have that big of a fleet in the field yet. But you can see that at least in simulation, we can shift electricity consumption from the blue dashed line, which is our best understanding of what a certain manufacturer's product would do with no load shifting, to the green line, which represents what happens with LBNL CTA 2045 signal schedules. And in that case, we were able to shift 77% of the electricity consumption out of the high price period to lower price times of day. And actually, if you look at that plot, as I'm sure nobody who lives in California will be surprised to hear, it really closely matches up with when we're producing entirely too much solar power that we need to absorb. So there's kind of a double benefit there. And through doing this, we were able to reduce the cost, the electricity cost of operating these heat pump water heaters by 29%. So there's a lot of motivation for people to participate in these programs because it'll reduce their utility bills. So we did some field testing in the CalFlex project with 10 different heat pump water heaters. I'll point out that these were the 120 volt plug-in ready products, which is really important because California currently has around 7 million gas water heaters. These devices are designed to make it easier to replace those gas water heaters with heat pumps, which has the potential to dramatically increase California's peak problems as suddenly water heaters are consuming electricity during peak instead of gas, right? So it's really important that we can provide something useful for these particular products. Now, one other thing to point out is that these products use CTA 2045, not CTA 2045B. So we did not have access to the advanced load up command. And that limits our ability to pre-charge the tank, you may recall. We can't increase the set temperature, so we can't store as much energy. Now, I'll point out this price curve that we use in CalFlex was called the Summer Highly Dynamic Price. And you'll notice that it's very inexpensive electricity, all the way down to 3 cents per kilowatt hour until around noon. And then it's gradually ramping up all the way to a peak of 78 cents per kilowatt hour. And this is designed to represent the cost of operating California's electricity grid on hot summer days. We recognize nobody's paying those prices, but this is what the grid is paying, really. And so it's important to understand our potential there. So we put that into the algorithm. We got out the load shifting control strategies. We sent them to 10 heat pump water heaters out in the field. And the second plot shows the resulting load curve. You can see that we dramatically reduced electricity consumption during that high price period. But actually, as you start looking at roughly 11 p.m., not all of the water heaters could make it through the entire high price period without the advanced load up. And so some of them actually came on earlier. But even with that downside, the vast majority of load was shifted from the high price period until just after or until the early morning hours. And simultaneously, when you look at the cost, right, since the price was so high during that high price period and much lower late at night or in the morning, we were able to dramatically reduce the cost in the high price period while having negligible impacts on the cost during the other times of day. So this enabled us to shift 52% of the electricity consumption out of the high price period to other times of day and reduce the cost of operating these water heaters by actually 46%, much higher than we had predicted via simulation. So that was a great start, but we recognize that people these days are shifting load in response to their current electricity prices. So we did some additional study looking at current California time of use rates. Noah, could you time check me really quick, please?
Yes, absolutely. 2:49. I think you should have about 3 to 5 minutes.
I'll speed up. Okay. So we looked at 3 different prices, and I want to really highlight, we were looking at characteristics of the price curves, not doing a comparison from one utility to the next. So just given that we've chosen the different price curves from the different utilities, don't make that comparison. It would be unfair. But we really wanted to look at one electric vehicle rate because these are rapidly becoming more common and they have very high peak prices. We also wanted to look at one with a reduced midday price because we theorized that would encourage shifting load to the low price period. And we also looked at one with a gradually increasing electricity price because these are kind of the norm in California right now. So if we look at just one example, which is the reduced midday rate, you can see a couple of results here. One is that all of the heat pumps did, well, not all, but most of the heat pumps did turn on right at the end of that lower price period. And what's going on there is that the algorithm's responding to the high differential in price that's about to come, as well as the fact that midday is the lowest price. And so it was using the load up command to charge up the energy in that tank prior to the price increasing. Then it shifted through the high price period and was able to reduce electricity consumption by about 29% prior to the price reducing again. Then when the price reduced again, we did not notice any evidence of snapback. And that's probably because the heat pump water heaters were fully charged at the start of the high price period. And the high price period is honestly fairly short. So we didn't have that problem. And then we were also able to reduce the electricity cost by 19%, which provides motivation for people to participate in the program. Also, I'll point out 19% is not the, what was it, 52 we had a moment ago. And that's just because the delta in prices in the CalFlex price is gigantic, right? And so a higher delta in prices encourages more load shifting. We also wanted to go back and look at an important detail here. Since these were CTA 2045 capable, but not 2045B, they didn't have the advanced load up command. So we wanted to figure out how well this would work if we did have access to advanced load up. And we went back to the simulation environment to evaluate that. So on the left, that's results without advanced load up. On the right, that's results with advanced load up. And you can see that the advanced load up did engage in the case with advanced load up. And I point out the 40 and the 80 above those plots to really highlight that the y-axis for electric power without advanced load up gets up to 40 kilowatts, and with advanced load up, it gets up to 80 kilowatts. So we were doubling the electricity consumption of that low price electricity in the morning. Because we were able to do that, we were also able to reduce the consumption during the high price period significantly more, just relying on that energy that's stored in the tank because of the advanced load up command. This dramatically reduced the cost of operating the water heaters during that high price period, and increased the cost of operating the water heaters during the low price period by, looking at this plot, I would argue, an absolutely negligible amount of money. And so because of this, the advanced load up increased the operating cost reduction from 32% to 53%, so a good 2/3 increase. We reduced the peak kilowatt hours instead of 29% by a full 60%. And we actually increased the consumption during that solar peak window by 65% with advanced load up instead of 14%. So last slide, Noah. Just some key lessons we've learned from this project and some of the stuff we have coming up next. First off, we've learned that price responsive load shifting for heat pump water heaters is possible today. We have all of the capabilities we need. We have control algorithms that we can use to make it work. Let's go do it. We also learned that you can do a better job of load shifting and reducing people's utility bills if you have the advanced load up command, right? In that one example we showed, it's 53% reduction instead of 32% reduction, and that's pretty huge. We also learned by comparing the results with different electricity prices that large changes in price throughout the 24-hour period yield more load shifting and yield more utility bill reductions. Now, one thing I didn't talk about in here, but I heard previously in the manufacturer panel, is that the CTA 2045 module and installation costs pose challenges, right? This is money that people have to spend on the module, and this can be kind of confusing for the average person to get the product, install, and configure it. So we really recommend that there be some load shifting capability on the water heater ready to go when it comes out of the box for $0. That's a lot to ask, but I really do think that's a big part of getting this to take off a lot more. Now, where we're going next, we have a project that we expect to start up in 2025, where we'll perform laboratory testing. We will also be expanding to look at more manufacturers as we understand more about how different manufacturers' products work. And we're starting to provide deployment tools to utilities late this year and early next year. And this is all in the effort of working towards making it easy for utilities to include these technologies right in their programs. So thank you, everyone, and I'll stop there.
Thank you so much, Peter. Great job explaining a lot of complicated technical information and a big study in just a very short time frame. One quick clarification question. Somebody asked when the study with 278 heat pump water heaters was.
That
question popped up during Geoff's presentation.
Yeah, so that was 2017, 2018. So BPA, PGE, Puget Sound Energy, Seattle City Light, Clark PUD, PGE, and Pac Power.
Great. Thanks for stepping in there. And then, yeah, I think Peter mentioned the first LBNL study he worked on was 2020. So yeah, this is all relatively recent, but we're trying to figure things out quickly so we can scale. And speaking of scaling, we have Amelie's presentation where we kind of go from pilot to a larger scale deployment. So with that, welcome Amelie, and I'll turn it over to you.
Great. Thank you so much. Noah, let me get my screen up for you all. And get you out of the way. Okay, you should be able to see my screen, right? Awesome. And you also hear me, which is great. Great. So let me dive into it right away. In the interest of time, I will be sharing some lessons learned from PG&E Water Saver program, which is a large-scale pilot program in PG&E territory, like the name implies. Before I get into that, I want to say if you live in California or if you know someone who lives in California and receives their electricity bill from either PG&E or SoCal Edison, there is a daily load shifting program available for you. You have information here on the slide. Please visit the websites. We'd love to have you take part in those programs. That would be awesome. All right. Load shifting, why are we doing this? How are we doing this? So the first thing is, and let me get those out of the way. I don't know if you're seeing them, but they are bothering me. Like Geoff said, what we're doing is we're trying to address the duck curve, and that means moving energy from peak demand time to the middle of the afternoon when we have peak PV production. That's because we're in California, and so that's when we want electricity usage to happen. How do we make that happen? First of all, we need to connect to heat pump water heaters and electric resistance water heater, but here I'm going to talk heat pump water heater only. How do we connect to them? Two options. Either we use manufacturer's API or we use CTA 2045. We cover both options because we want to meet manufacturers where they're at. In the case of CTA 2045, the program pays for the UCM and we provide them free of cost to our participants. So there's no barrier for participants there. It's covered by the program. At the moment, we have a majority of devices connected via API, but the number of CTA devices is growing pretty quickly. Once we're connected to devices, we place them in load shifting groups. We're not yet to the level of what Peter just presented. We hope to get there next year once we are able to, get that collaboration started. But so for now, what we're doing is we have two load up options. The first one is basic load up, where we're just topping off water heaters to the user set point during the load up period. And the second one is advanced load up, where we're storing extra energy during that load up period and exceeding user set point. This option obviously is only available for participants who have a thermostatics mixing valve to avoid scalding risk to our participants. And then in terms of shed duration, this is based on participants' electricity rate. Because this is PG&E, we have a 4 to 9 and we have a 3 to 12 a.m. This is for the ELEC EV2A rates. And that covers peak and part peak for them. And in terms of shed, we are using the shed command, which is a light shed. So we're not turning off the water heater. And that's because we want to minimize the risk of cold water events for our participants. Again, customer comfort is very important to us. All right, and once we've placed people in those groups, what we're doing is just sending commands to the device to load up and shed. And this is an illustration of what happens when we send those commands to devices. The two at the top are what happens when we send an advanced load up command. So you can see the green light, is the user set point. The blue line is the actual tank temperature. So you can see in the case of advanced load up that we are exceeding the user set point, the initial user set point. In the case of basic load up, we are not. We're just topping off. And then during shed, we're decreasing user set point basically, and then we're just coasting through that period with the hot water that we stored previously. All right, so these were just illustration. Now that you know how we're doing it, let's get into the results that we are seeing. So the first one that I want to share is basic load up. And basic load up, as Peter talked about, what happens is we have a post-shed snapback, basically, which is not really controlled. And so what happens for California, at least, is that we're ending up prolonging the peak. We're moving energy usage from peak period to right after the peak. And in California, right after the peak is still very high GHG content. So that's not ideal. The new thing that we're doing in Water Saver that very few programs have done before us is advanced load up. And so with advanced load up, what we're doing, again, is we're storing extra energy for people who have a thermostatic mixing valve on their installation. And as you can see, in the case of our 4 to 9 shed group, we're able to coast through the whole shed period. And we don't really have a post-shed snapback anymore. So we're really able to store enough energy pre-peak to be able to go through that whole period. And then for the 3 to 12 group, so what you can see is with advanced load up, we are able to do much longer sheds than if we were just doing basic load up. In that case, we do have a small snapback, but it's definitely not as bad as the BLU group. So that illustrates how important advanced load up is to load shifting and being able to really use energy when we want to use energy. This is a recap of the results that we're seeing. So advanced load up is the one that provides the most savings, like the most energy shifted out of shed. It is the one that provides the most energy shifted to peak renewable as well, and the most peak reduction. The thing with advanced load up, though, is we are sometimes increasing energy usage for our participants if we're loading up too much, basically, during that load up period. And depending on your electricity rate, that may lead to bill increase. So it's not the silver bullet yet. It is definitely the solution that we need to explore, but we don't have the perfect algorithm yet. And that leads me to some of the challenges and recommendations that we have for the industry at large. And we're definitely working on some of those recommendations and implementing them right now, including with some of you on this call that I've seen before. So the first one is that advanced load up is not available for everyone. Like Peter said, this is restricted to CTA 2045B. So we need that 2045B. It is important because it's the only one that covers the ALU capability. We also need thermostatic mixing valve on installation. And then the last point that we haven't talked about so far is we need the water heater set point to be below the maximum allowed by the manufacturer. Because if the user set point is already at the maximum allowed by the manufacturer, we're not going to be able to store extra energy in that tank. The manufacturer won't allow us to do it. So it's important that those set points are set below the maximum allowed by the manufacturer. And as you can see, in our program, we currently have about 320 plus water heater. Only half of them, slightly less than half of them, are really able to do advanced load up. So that's the first thing. The second thing, and that goes towards why are we seeing an increased energy usage, is the fact that at the beginning of that advanced load up phase, and then at the beginning of the post-shed recovery, we're seeing an increase in resistive element usage for the heat pump water heater that have one. The way to address that is to be able to specify the efficiency mode of the heat pump during this period. Now, the thing is, under CTA 2045B, this is an optional command. So we know that some manufacturers do support that command, but not everyone supports that command. We need to get to a place where everyone supports that command. All right. Like I said, increased energy usage as a result of advanced load up is an issue. If we're able to be energy neutral, then we're sure 100% that our customers will see savings. If we increase energy usage, then depending on the time of rate structure, we may see an increase in scales. And that's just not acceptable. It's not acceptable for the customers, and it's not acceptable for us if we want to scale our programs. So there's two things there. One is we are working on making sure that Advanced Load Up is energy neutral. But in addition to that, we also need to have rate structure that incentivize energy usage during peak renewable production. So if we go back to Peter's presentation, we need electricity rates that basically have a lower rate in the middle of the afternoon when we have large renewable production on the grid. One thing to note here is we do have monthly participation incentives that do cover those bill increase for our participants. So we have that covered. All right, I'm just doing a quick time check. The last two challenges are a bit more into the weeds, but I know they'll speak to some of the participants on the line. So the first one is the fact that when I'm sending a command, what the device does as a response to that command varies by manufacturer and varies depending on how I'm connected. If I'm connected via API over their CTA 2045. It's a bit all over the place. The example that I will use here is the shed command. We're seeing some devices lower their set point by 6 degrees Fahrenheit, 10 degrees Fahrenheit compared to user set point. Some are just their set point to 110 regardless of the customer set point, and some just increase their deadband, but there's no change in set point. All of that makes for a very different user experience, and also it makes it complicated for us to evaluate if our programs work and if they're beneficial to the customers. Part of the reason is because the standard right now doesn't give any guidance to manufacturer as to what they're supposed to do in response to those commands. And so we think an answer to that is to move to a conformance standard, which would say, we want you to answer to a shed command this way, right? And then the last challenge that I want to put out there is data access, command access, and data quality. So it's not just manufacturers that have to get up to speed to CTA 2045B. It's also the UCM manufacturer. It is also the DERMS provider that needs to get up to speed on that one. Because what we've seen is that even though we're supposed to have access to more commands and more data with the newer standard, it doesn't necessarily show on the DERMS platform that we're using for our programs. So that's the first thing. And then the second thing on data quality is so we rely on power data that the devices send back to us to know, to calculate our program impact. And unfortunately, again, this is a bit all over the place. Some manufacturers give us very precise power numbers. Some manufacturers give us static numbers. I would say I would be fine with either. I just want to make sure that those numbers are pretty accurate. And so I think we need to have accuracy targets for this data that we get back. All right, that was the last challenge that I wanted to cover with you. With all of that, I mean, we need advanced load up. We need thermostatics mixing valve, basically, to be able to shift energy usage to when we want it to happen. And beyond that, really, load shifting is an optimization game. And yeah, that we have to figure out, and we're figuring it out together. All right, that is it for me. I think that leaves us a little bit of time for questions. Hope I didn't go too fast on that one.
No, that was great, Amelie. Thanks so much for running us through that. Great job to all three of our presenters. Really appreciate it. And we have about 10 minutes left. So just wanted to have a few questions answered. I think the first one was, kind of how quickly or does it ever pay for itself, meaning buying a universal communications module, putting it on the heat pump water heater, and then running these kind of load shifting commands. I will let Geoff speak to that first, and then Peter and Amelie, if you want to jump in as well. But kind of what is the payback here? Is it worthwhile currently from a purely economic perspective?
Well, so there's lots to deal with here, Noah. But my gut response is yes, it does. I think you need to talk about what costs are you including and what costs are you avoiding. How much does it cost PGE, Portland General Electric, to have a blackout and shut down the fab for Intel, Fab 4 and Fab 5? That's millions of dollars, and that's a big lawsuit. Or how much does it cost to shut down the city of San Francisco during an outage versus how much does it cost to install UCMs at volume? And we see prices at $50 to $60 for UCM and $3 per year for communication for connectivity with a cellular module. So very inexpensive. And when you think of all the infrastructure out there, once you start getting to 1,000 or 10,000 a megawatt hour, it starts becoming very cost effective to do this kind of thing. I'll let Peter weigh in. He's got some real numbers, I'm sure.
I actually don't have that many real numbers for this one, Geoff, unfortunately. But so I'll give the most scientist answer you could possibly hear to this one and just say it depends, right? In areas where you just have a flat electricity price, then load shifting is not going to save anybody. Well, it's not going to save the homeowner any money, so it won't pay off, right? But if we start looking at the CalFlex scenario where these highly dynamic prices are going out to the device, there's a delta from 3 to 78 cents per kilowatt hour throughout the day. We've estimated that it could pay for itself in approximately 1 to 2 years. That said, I do rather agree with Geoff's comments that to a large extent, the value comes from utilities running programs where they are paying for the module themselves, and then the utilities are offsetting their costs using the load shifting, which I won't provide numbers for because I'm sure Amelie can do a better job than I can.
I love how this question is going down the line. So, I mean, like I said, in the case of Water Saver, and it is the same for Smart Shift Rewards, the utility is paying for the UCM module. We're not paying for the CTA port on the water heater. That obviously is integrated in the cost of the water heater, but we are paying for the UCM module that goes on top that we need to communicate with the water heater. And I will say that based on the calculation that we've done in terms of grid benefits, the cost of the module pays itself very quickly from the utility perspective, as in less than a year.
Excellent. Yeah, thank you three for those good answers. I think it can be maybe daunting to pay that extra anywhere from $50 to $200 depending on your order volume. But yeah, there are a lot of benefits, and that's not even tracking things like avoided greenhouse gas emissions, right? That we might get into more in the future. And yeah, another question is just kind of scaling up. So what are y'all 1 minute takes on how we get a much higher percentage of heat pump water heaters enrolled in programs like these, and especially for new heat pump water heaters that are installed, because that's going to be the bulk of all of them, right? As we really grow this market.
Sure, I can take a stab at that one. So in California, you may be aware that the Tech Heat Pump Water Heater program, which is a program to incentivize installation of new heat pump water heaters, is going to be relaunching pretty soon. And in that new iteration, enrollment in a load shifting program will be required by the program. So basically, it's going to be like a straight. You install your heat pump water heater, you enroll in the load shifting program. So that's one way to really grow the participation in that type of program for sure.
Awesome. Thanks, Amelie. Peter, Geoff, you want to chime in too?
Yeah, so I would argue that, anytime we want to increase adoption of a technology, in addition to requirements like Amelie was talking about, two great levers to pull are increasing the desirability of the technology and decreasing the hurdles of the technology, right? And I think if we have time of use rates, with a very large differential in price from that noon period where we are overproducing solar to that evening peak period where PG&E is at risk of not being able to meet demand, or Edison's at that same risk, suddenly people are going to be actively looking for ways to shift load. And suddenly it gets a lot easier for Amelie to do her job of recruiting participants because they're actively looking for it. Also, I did mention earlier about the module installation. And the more we can make it easy for people to participate because the water heaters are ready to go out the box, just the easier it is to get everything installed and communicating and ready to go.
Great answer. Geoff, did you say you're trying to share your screen again?
Yeah, for some reason I've lost that button. I don't know where it went. I was going to show you this label, and we've started checking this out with the manufacturers. There seems to be very positive interest in this. The label would go on every connectable water heater that ships out any factory, and on that would be a QR code, which would then enable the installer to say, what's in it for me? And then that installer is going to say, let me show Mr. Customer what's in it for you. And then through that process, the customer enrolls and says, I'm going to give you my name, address, location, a picture of my meter, my electric meter, and a picture of the nameplate. The value to the utility is they've got a program, they can enroll it, and or they actually, why is it not showing I want to be able to show this one sticker. So it's not this particular one. But then the customer then enrolls in a program if one exists. If one does not exist, OpenADR Alliance will hold this flex load location or this customer as interest and say, gosh, we've got 11,000 water heaters in your service utility, Mr. Utility. Would you like to enroll and or engage with them, and let's stand up a program? The manufacturer gets the value that they get to know when and where their water heaters were installed and what date. And then we can continue to stay active and enrolled in those things. And we're not talking about demand response programs. We're talking about flexible load management, much like what Amelie and Peter were talking about, every day doing small transactions. And in the background, no one will really know. So that's one side. The other side is it's an opt-out program where every water heater comes ready, enrolled, either has a cellular chip or an FM chip, and it's already there, and the customer has to enroll out of the program. They're already enrolled in. So there's two options.
Yeah, that's a great point, Geoff. And I think that really goes for programs across the board. Having folks opt out is more work, right? Same thing goes for TOU rates in California. So with that, we're right about at time. So thank you, all three of you. That was really excellent presentations. Someone said in the chat that a lot of the passion for load shifting comes through, and I think that's absolutely the case. And I think Joe shared some slides earlier that there are more resources out there. There have been a lot of cool pilots in the last 5-10 years. So if you ever want to read more, there are readily available resources that are linked in the main deck. And with that, I'll turn it back over to Joe. I'm assuming it's break time.
Right. Thanks all. Thanks so much for that fantastic panel. Thanks, Geoff, Peter, Noah, and Amelie. Really appreciate that dive into load shifting and heat pump water heaters. Really great stuff. We've got another quick survey for y'all to fill out. If you don't mind, we'll put it in the chat. And we're going to take 10 minutes before our final panel on 120-volt water heaters. Thank you for sticking with us. It's going to be a great, great session. You don't want to miss that. And then we'll have our heat pump water heater dance party plus the raffle drawing, and we'll close out Heat Pump Water Heater Day in style. So stay with us for the next 10 minutes, and then we'll see you at the next session. Thanks so much.